Section 4.3, we're going to be taking a look at greatest common divisors and least common multiples. So we're going to start with greatest common divisors. We've actually talked about these a little bit, but now we're going to define them formally. So the greatest common divisor or greatest common factor is the greatest whole number that divides all numbers in a set. And we finally get the phrase that I keep using, relatively prime, again, formally defined. Two numbers are relatively prime when their greatest common divisor is 1, or you could say when they have no common factors other than 1. So some examples of relatively prime numbers. I'll give you a couple of them here. 6 and 7, those would be relatively prime. They only divide by themselves, they only divide by 1, right? We could do 10 and 10 and 9. So 10 and 9, neither one of them are prime, right? But they are relatively prime because it's a comparison kind of thing. Compared to one another, they don't have anything in common. So we call them relatively prime. All right, so the rest of the greatest common divisor portion here is going to be showing you different ways of finding greatest common divisors. And kids encounter these at different levels of education, all right? So the one that you're probably most familiar with because you've been to high school is the last one we're going to talk about, I think, okay? So I'm going to show you some more intro kind of level things that kids see earlier on. The first one is going to be intersection of sets. So intersection of sets works when the numbers are fairly small. And what we do is we list the divisors of each value, and then we find the largest divisor that they have in common. Okay, so if the numbers are really, really big, this is a very beastly kind of way to do this. We don't want to do that, but that's not usually what's going on. The whole point is they're small numbers that we're talking about when we see this method. So we're going to find the greatest common divisor for 12 and 15 using intersection of sets. So what we're going to do is we're going to write down 12 in pairs. So for example, 1 times 12, those multiply to give me 12. And 2 would also would divide 12. 2 and what give me 12? 6. 2 and 6. And then we can do 3. 3 and 4. And if we have done this kind of in order, like for moving this direction, what ends up happening is we can go back this direction and we're done, right? It kind of loops around whether you draw it like this. I think when I did it before, I did a similar question with the 24s back in section 4.1. I did it vertically maybe, but they're all there, and I can see that they're all there because I've done them in pairs. So let's do the same thing with 15. So 15 would be, 1 and 15. 2 doesn't work. 3 does. 3 and 5. And then 4 would be the only other thing that's sort of in between 3 and 5, right? If I go sort of around like this, there's no more space. So these are the only factors of 15. And then what we're looking for is we're looking for what they have in common. The biggest number that they have in common. And what's the biggest number in common to both of these sort of looped lists? 3. So the greatest common divisor is 3. Okay, we're making lists. Okay, so let's see what I did. Okay, so I take it back. The next method's the one you're most familiar with. I couldn't remember where it fell on my list of numbers. There's 2 other methods after this. Prime factorization is what you usually see showing up in about junior high somewhere, depending on your curriculum. So you construct the prime factorization of each number. You look at all the prime factors that they have in common, all of them. And then you list each prime factor with the smallest exponent that any of them have. And then you find the product, which means you multiply them together. This method works really well in that junior high age because kids are entering algebra. And this parallels really well with what you do when you're doing this with exponents. With variables that have exponents. So that's usually why it sort of comes back around in junior high, is not because you're really wanting to do it with numbers, but because you're leading up to doing this with exponents and finding common denominators and things like that. That's usually what we're looking for when we see it happen in junior high. So we're going to do an example again with numbers, but you can see the numbers get much bigger. Doing this with 12 and 15 would be very simple. I mean, it would be very simple. But the process wouldn't really make a lot of sense. You'd look at it and you'd go, why did I do that? That seems really weird when I could have done it by just listing things out. I don't know about you, but I don't want to list out all the factors of 400. There's quite a few of them, okay? The numbers are much bigger. They don't work very well for that first method. So the way that this works is we take the numbers, in this case 400, and then we have 360. And we break them down into any factors you want of 400. So you might look at this and say, well, 400 is 4 times 100. You might have looked at that and not thought 400 at all. You might have thought, 10 times 40. Or you might have looked at that and said 2 times 200. It doesn't matter. Just break it down into something. And we're going to keep breaking things down until we get to primes at the end of the breaking down. Like 4 is 2 times 2. Those are primes. And when I get to the primes, I kind of like to circle them so I don't lose them. Okay, 100. Okay, well, I can do 100 as well. 100 is, 10 times 10. Or you could do something different, but 10 times 10 works. 10 is not prime yet, so I can do 2 and 5 for each of these. Okay, so there's all my prime factors there. I've shown you factor trees before. We did this in an earlier section, in section 4.2. When we get to the end of this, we can say, oh, look, there's 2 and there's a 5. And then we need to count how many 2's there are. So how many 2's are there?
4.
There's 4 of them, so this is 2 to the 4th. And how many 5's are there? 2, so it's 5 squared. I can do 360 with a factor tree as well. So feel free to use a factor tree if you like that strategy. I'm going to do the division algorithm that I also showed you in the previous section, just to remind you that that's an option too. The division algorithm actually goes by primes. So we're specifically looking at dividing it by the smallest primes. So in particular, this will divide by 2. If I take 360 and divide by 2, I get 180. And I can divide that by 2. And I get 90. And I can divide that by 2. And I get 45. I no longer divide by 2. 45 is not even. 5 works, but there's a smaller one that works. 3 will actually divide 45. 45 divided by 3 is 15, which will divide by 3 again, and then give me 5. And then if we collect them all again here, I've got 2's and 3's and 5's. How many 2's? 3. How many 3's? And how many 5's? Okay. And I'm going to write the 1 for now. So either of those strategies, pick your favorite, doesn't matter. Those really aren't different strategies. They're different pictures of them. Okay, so here's what we do after this. So all we've done right now is number 1. Step 1, we have done the prime factorization. Step 2 says, look at these 2 prime factorizations and see what prime numbers as bases they have in common. What do they have in common? 2's and 5's, right? So the greatest common divisor will be a 2 and a 5, at least partially. The second thing that we have to do here is we have to list, it's step 3, but the second thing in this process is to list each prime with the smallest exponent of any factorization. So if I compare this 2, it's 2 to the 4th, with this 2, it's 2 to the 3rd. Which number's got smaller exponent? The 3, right? 2 to the 3rd. So this GCD will have 2 to the 3rd. And then I look at the 5's over here. This is 5 squared. This is 5 to the 1st. Which exponent is smaller? The 1. So we put the 1, right? And then the last thing to do then is to multiply that out. Well, 2 cubed is 8. 5 to the 1st is 5. This is 40. 40 is the greatest common divisor. That is prime factorization method. And we'll stop there for today.